Okay, I'm recording. So.
Okay, cool. So yeah, why don't we just take a look at your questions first, Cody?
Okay,
since that's when we
so
start, and I'll probably just be
the
up here by the
question-
board.
Okay,
Which lesson?
this is lesson 15.
15?
Mm-hmm.
Yeah, that's just the review.
That's just reading.
Mm-hmm.
So this will be. I'll just talk about margin of error like generally, because you
Mhm.
do it for a lot of the different tests.
Right, and there is no way to do it on SPSS.
You just take the
No.
lower minus like the mean or whatever.
Yeah, so a really easy way to do it
Okay.
is you. A lot of times it'll calculate a confidence interval for you, right?
Right. Mm-hmm.
So you can just take the upper limit
Mm-hmm.
and subtract the lower limit and then divide by 2. That gives you the margin of error. Now, does it make sense why that works?
Yeah.
Why don't you just run me through that? Like, why does that work to get the margin of error?
So that will work because we're able to find the differences between them.
Yeah.
Right.
Well, so I'll just draw it out. So the margin of error, the way you get a confidence interval is you have like a mean, something in the middle,
Mm-hmm.
and then you add the margin of error to it, right? Or you subtract the margin of error, and that gives you the end points here. And it doesn't tell you what this is, and it doesn't tell you what this is,
Mhm.
but if you know what this and this are, you can subtract these two, and that gives you this whole distance right here,
Okay.
and then you just want half of that, so then you divide by 2.
Okay.
And so that's like a really easy way to get the margin of error for like any test you're doing, any problem they give you, like if they give you the confidence interval, this works for finding the margin of error for confidence interval.
Okay.
Otherwise, the way you do it is you have you have the formulas where you can do z star over or multiplied by sigma over the square root of n, or t star. So anytime I ask you a question, it's for either of you can answer. But how do you find out what z star is when you're doing the?
It's on the chart.
Okay, yeah, there's a chart.
Hey guys.
Hey Moroni.
So I
Moroni's
called
gonna
her.
hop in on this.
I called her and she was like, I've been listening else.
Sorry about that.
No, it's okay.
So we're just talking about margin of error right now.
Okay.
So just to kind of quickly recap for you, like for any test that you're doing, a really easy way to calculate the margin of error is just to take the upper limit of the confidence interval, subtract the lower limit, and then divide by 2. And that'll give you margin of error. Now we're just talking about where z star comes from. And so you're right, there's a chart, but say you didn't have that chart. With the normal probability applet,
Okay.
you get this guy right here. And then it has this section called area. What you can do is if it asks for, like say it asks for a 95% confidence interval, you come in here and you type 0.95. And then it'll spit out a z-score right here. And it'll say 1.96. Or it'll say negative 1.96 and 1.96. And just be sure to shade in the middle when you do that. So that's a way, I think what you had was, I think that's the easier way, just to do a chart and just memorize it, because it's always the same.
Yeah.
Like it will always be 1.96 for
Mhm.
95% confidence interval, and it'll always be 1.645 for the 90 and
Okay.
2 point something for
This one's supposed
Okay.
the 99. So those are always the same. But if you, for whatever reason, aren't able to remember, you can find it with an old probability applet.
Okay.
So,
And then I have like some other questions. Like apparently I didn't do this right on SPSS.
okay. Well, let's take a look at it.
So it's on. Let's see.
Oh, yeah.
Those two formulas below are
These are for margin of error. So this is if you don't know what the confidence interval is, this is how you calculate
Okay.
margin of error. And I was talking about how you figure out what Z star is. That's this number is Z star, but you only put the positive one.
Yeah. What do you call this? Z star?
Because that's how they notate it. Like it won't say Z, it'll be like Z star in the textbook. But
Yeah, because the lower and the upper were wrong, but this was right for this question.
Which one was it?
Like questions 7 and 8.
so if you look at it, you were really close on these.
Right,
So my guess is it's a rounding error somewhere. Let's.
because that's
Did
like,
you do this at SPSS or did you do it by hand?
I think this one we did it by hand.
It looks like you did this one by hand.
Yeah.
Why don't you all kind of tag team this one on the board? I'm just gonna erase this.
Mm-hmm.
I want you, all three of you, to take a look at this and try to work it out on the board. And
Okay.
just start from margin of error
Mm-hmm.
and calculate it. And do you need a calculator? Because I can loan you mine, but you're gonna want to try to not round.
For our class,
Yeah.
what are the notes we can take in?
What are the notes?
Page or 3x5 or
Are you in the class with
think
Brother
You
Richmond?
just get a note card.
I'm in
I
on
don't
that.
even.
Uh-huh.
2x5?
I'm not sure.
Oh, you don't know who
Teacher?
it's by. Oh,
No.
Okay.
Okay.
Because if you're in that one, for this exam, we're allowed, because SPSS isn't working for VMware.
It's working now though.
Yeah,
Oh,
they
it is.
said it was.
Yeah,
Okay.
they fixed it. So the
Okay.
testing center's working and
Okay.
SPSS is
That's
working
good.
now. So yeah, why don't you all three take a look at this one and then try to work it out on the board. And I put my
Okay.
calculator here, so
Okay,
if you want
thank
it,
you.
you can use it.
Okay, so
We'll also work together on this.
we have sample 1,000. So we'll go Z star. Will we use this one or you use the T?
So you use just that one right there.
Okay. So,
You just find what you have.
mhm.
Like see whatever equation works best. Yeah, so you get that.
So do we go? So would this is the standard deviation like n here or
Yeah, it says it right in the problem.
right there, right?
Yeah.
Okay. And the sigma is 0.01, is that right?
No, that's your standard deviation. It's a sigma.
Okay.
Because what you put your n
Mhm.
is the population. So it says,
Okay.
let's see. She randomly selects four
Four.
drive shafts. So
Okay.
that's your.
Okay. Equals 4. So
Yeah,
it's
then your standard deviation is 2, which is
okay.
sigma.
Okay.
So it's
So it's just 2 divided by 4.
square root of 4.
Oh, the square root of 4.
And you'll still have to times that by the z star, whatever it is.
What do you do square root of 4?
Is that
What do you do the square root of 4?
y?
Yeah.
Because in the equation it's z star
Mhm.
times sigma over square root of n. So do you see where I got n from? Do you know what n is?
Yeah.
What is it?
N is the population.
So what would be the population out of that?
Okay. Air. I think 2 times.
Oh, for dry shit. Okay, I can see
Do you
that.
see where that came from?
So our z star, isn't it 1.96?
Mm-hmm.
So that's the margin of error. And then how do we calculate the upper and the lower bounds?
So then all you do is see that's where it says the standard. Where would I move on? It says normally it's 1,000 or so. So then margin of error is from the 1,000. So subtract it and add it, and that's your lower and upper.
Oh, from 1,000?
Yeah.
Okay. So 1,000.
I have a question on 12 on here actually.
Cool. Yeah, let's take a look at it. But does that make sense? How you
Kind
get those answers?
So I just go 1,000 minus 1.96.
Mm-hmm. And that's your lower. Then you go 1,000 plus. That's your upper.
And see how
And then I
that
times
matches
it by
up.
1,000.
And then you just leave it.
Uh-huh.
So that's the lower.
Mm-hmm.
And then for the upper, you do the same thing, but here you just add. And see, let's take a look and see if that matches. And it does. So like, okay, golden.
Mm-hmm. So I don't know what we did last night. But thank you.
Not for sure. I mean, it's possible you like just mistyped because you have 6-9. You could have done that
Mhm.
instead of
Yeah.
6.
Yep. Okay.
Yeah, that's a really good 12.
Perfect.
Yeah, I got a question about this.
Okay.
So why is it this? Because I know it's talking about like the sample variance is nearly equal, and that's what we're looking for in a ANOVA.
Yeah.
But it should be right skewed. But why does it say like that are bell
Okay.
shaped?
So
What question
I
are you on?
understand what
12?
you're saying.
Okay.
So the ANOVA
I'm
test,
confused by that.
this is like, so you're right that the what's called the F distribution, what the ANOVA test uses is right skewed.
Yeah.
But the question isn't talking about this guy. Like you use this to do the test, but what it's talking about is you have like a set of data. So you have like a bunch of observations that are whatever, and it says, are these normal? Because you make a ratio out of these and then compare it to this, and that's how you do the ANOVA
Oh,
test.
so the data doesn't.
So it's
have to be
asking if the
skewed or
data,
something?
yeah, the data doesn't have to be skewed.
Okay.
So it's awesome that you're remembering that from the textbook. But like data, you always want data to be normal. Like normal data is always good. That's a good
Does it
question.
mean it's not biased
Yeah, you could say
in
that.
some way?
Yeah, like
There's no any outliers or
yeah, exactly.
Okay.
That it, the math works well. We'll put
Yeah.
it that way. I won't explain too much.
So what is that F then? So when is it right skewed then? Because I know it's just that's
So
what they said.
yeah, in the textbook they explain that the F distribution is always right skewed.
Yeah.
How to say this? Well, think about like when you do like a z-test, you can get a z-score. Like you calculate your z-score by doing, you do x bar minus mu sigma pi by square root of n, right? So this number in theory can be negative, right? It's like this can be, you can get a number on top that's negative. And the bottom will never be negative. But so this can be a negative number. So it goes both ways, right? Like the Z distribution looks like that. With the F distribution, what you're doing with the ANOVA test is you make a ratio of variances which aren't negative ever. So it doesn't go this way at all. And like basically the top doesn't change as quickly as the bottom, so the numbers don't go as high up. And so like as the bottom gets bigger, it just gets more like stretched out that way. So that's why the F distribution looks like that. But for this class, you don't really need to know this part. That's like the classes that I'm taking. Like they put that in your textbook and it's good to know. But like the parts that's important for this class is talking about like the data itself. Like you take a sample, are the numbers in that sample, are they like normally distributed? Are the variance equal? That kind of stuff. And then you do some math with this and then you get a ratio and you compare that to this. And then that's where
Alright, I see
that
where
all comes from.
that's coming from. Okay. Now I got another question.
Okay.
Let's see. Oh yeah, so how do we know how did we know this? Like there are 4 types of confidence intervals listed below. Which situation, like how do we know like just from this, like which one to choose or which?
Okay, that's a good question. So they're like a series of questions you should ask yourself. Like, first question, like you can ask is, do I know sigma? Do I know what the population standard deviation is? Because if you do that, it's automatically a z-test. Like, oh, I'm doing a z-test.
Okay.
The next question you want to ask is, how many samples did they take? So we'll make this like a flow chart kind of. So like if you answer no to question 1, then you go to question 2. It's like, okay, how many samples did they take? And then you have an answer to this question. You can do like, you can say 1, 2, or we'll just say, we'll just say more than 2.
Yeah, more than 2.
More than 2 is how we'll put it.
Yeah.
So then, based on how you answer this question, like, oh, if they took 1, then it's either a 1 sample T or paired, depending. If they took 2, it's either paired or independent. And then if it's more than 2, it's just ANOVA.
So you said 1 sample is did you say a T?
It's either a t-test or a paired test, assuming you don't know sigma. So then you can ask, like, how do I know which one of these to use? So say they get 1 sample. So you say, okay, I have 1 sample. Then you can ask, how many things are they looking at? Like, what's my stuff that I'm interested in? Because, for example, say you know that the national average GPA is like 3.2 or something for college students. But you think that BYU Idaho students have a higher GPA on average than 3.2. So you can go out and you can take 1 sample of 50 kids and find their average GPA and compare that to the national average. That's a 1 sample t-test because you don't know what the population standard deviation is. So you go, okay, I get 1 sample and I'm just looking at one thing, GPA. For paired, you could have 1 sample where it's like, say you're a teacher and you go to some conference and they tell you about like some special teaching method. They're like, if you teach your students this way, they'll do like 50% better in their classes. And so you're like, okay, I'm going to see if this works. So you take 1 sample of students, like you take a classroom, we'll say. And then for 3 weeks, you just teach them like normal. And then you have them take a test and see how they do. So that's your first stuff. And then you do another 3 weeks using the special method, and you have them take the same test or like a similar test, and you see if they're different. So you subtract the difference, and you get the difference between stuff 1 and stuff 2.
Yeah, okay.
So that's how it can be. That's what can happen if you have one sample group. If you have one sample, it's either one sample T or paired in that way. Does that make sense to everybody?
Yeah.
Okay. So now, going on from that, say you have 2. Say you are interested to see if marriage counseling can improve the satisfaction rating of people's marriages. So you take a sample that has 2 groups. You have husbands and wives.
So that would be dependent.
Yeah, exactly. That's dependent. That's paired testing. And you're looking at satisfaction, like a before and after satisfaction. Where it's like, kind of like, I guess it kind of looks like this. Where they're paired and you're looking at satisfaction before counseling and after counseling and seeing if counseling helped them enjoy their marriage. In the online class, do you do any projects? Did they have you do like a Subway in the Mean project?
We're gonna start that next week
Yeah,
or something
next
like that.
Okay. Okay. Well then, I'll just explain it. So this is a good example of independent right here. Where say you go to Subway and you order a sandwich, and you're just curious, you order a 12-inch sub, and you're like, I wonder if like this is actually 12 inches long. And you measure it, and it's 11 inches. And you're like, what the heck? Subway's freaking ripping me off. And you're like, you know what? I'm going to sue Subway because they're selling me 11-inch sandwiches and saying they're 12. And now you take in Subway to court, and they have to prove that they actually sell 12-inch subs. So what they do is they're like, okay, we're going to take some random samples. We're going to go to Boston. We're going to go to New York. We're going to just go sample a bunch of sandwiches. We're going to go here and we're going to get 100 sandwiches. We're going to go here and we're going to get 100 sandwiches. And we're going to see what the average sandwich length is. And so say it's like, say 11.8. And this one's 12.1. So then you're going to take these averages and you're going to subtract them. And it'll give you like a difference of these 2 means. And that's what you use to do the test. And so this one's independent because like if I take one sandwich from Boston, there isn't really a sandwich in New York that corresponds to that sandwich. Like if I pick a sandwich in Boston, I don't know which sandwich goes with it in New York. They're not connected at all. Whereas with the husband and wife, like if I choose a husband, I know which wife goes with that husband.
Yeah, cool.
Does that make sense for those 2?
Yeah.
And then the ANOVA test, it's straightforward. So I have more than 2 groups, so we're going to do the ANOVA test.
Okay. So I think there was only like one set of data, so that means like if that's true, that would just be one sample, right?
Well,
You have one sample, so it's either sample T or paired. So you pull this thing up, and that's just what it's asking. So by just having the one sample, so you either narrow it down to these 2, right?
Mm-hmm. Yep.
Then you either know if it's T-test or paired. Then how do you know if it's paired or T-test? Let's see.
So now
Sure.
what are you looking at? Do you remember when we drew the picture?
Common level of fear.
So with the T-test, you're just looking at one thing. Whereas the paired, you'll be looking at 2 things. there'll be like a before and an after, or a pre and a post.
Okay.
Mhm.
There's something there.
Okay, so it's not a before and after. It's just collected random swab samples in a field, measure that level is each sample, measurements recorded. Oh, so it's just measuring it one time. That's
So just
it.
one time. So for
Okay.
that example, you're looking at like, what was it, carbon levels in soil?
Yeah. So if sigma was known, it'd tell us like in the description up top.
Yeah, it'd
If
say
it
up at
would
the
say
top,
sigma
like,
this.
it'd say sigma is this, or like,
Okay.
it's
That's-
there's a known population standard deviation of this.
Yeah. Okay.
Just to clarify for you, like a way that example could have been paired data is if they'd said like we're interested in lowering carbon levels, and like, so I just made some sort of like treatment for soil.
That would be the
So like, okay, we took the carbon levels before the treatment, then we gave the treatment and did an after. Well, let's say we do that, gave a treatment and then like a little bit of time and saw if there was a difference in that. That would do it.
You would count it as paired or no?
What?
You would not count it as paired.
That one you would, because
Okay.
the soil would be the same. It
Yeah,
would be
sure.
looking at the same spot of ground.
So whenever there's treatment with the same population,
Mm-hmm.
okay, it's paired. Okay. Because the
It's
population is the
paired
same.
when like the things you're looking at predict each other. So like for that last example, like if I look at the spot of soil of ground before I've done the treatment, like I know which spot of ground I'm going to be looking at after the treatment. It's this chunk of ground.
Okay.
And then can you help me? I don't know what we did wrong on SPSS to calculate the test statistic and like get the p-value for direct flight costs.
Okay. Yeah, let's open up SPSS and we can take a look at it. Sorry, Marone, I use
Oh, don't worry.
Excel, but
Yeah, I know. It's not that different.
no, I mean it might
At
be
the end, do
helpful.
we have the same test?
Yeah, you basically have the same test. Like this test review is the same one you took for lesson 15.
Yeah.
SPS test takes forever.
Yeah, that's the one thing that stinks about VMware is it's kind of slow.
You working the next hour?
No, actually. I normally have student support office
Oh.
hours that I do then,
This is support.
but I'm actually not going to go today because I'm going to get engaged today, so
You proposing?
I am proposing today.
Where?
Just here in town. We're going to go for a walk after we do some other things. But
Okay, that's cool. I proposed to my wife at Grand Turkey.
nice. Like, what time of year was it?
Went snowboarding and
You went
we
snowboarding?
hiked Nares
Oh,
on top, and you have like
yeah.
Wyoming on one side, the Tetons, Idaho, and I proposed there.
That's awesome. Yeah, she's got like, my fiance has like this favorite spot in Rexburg that she likes to go on walks to and like just sit and like think about things. So we're gonna go there.
So we're comparing the data of Heathrow, and so we want to know like
Okay.
the cost there.
So what kind of test do we need to do here? And you guys can work on this too if you want.
So we need to do a dependent samples test, right?
Okay.
Then I need to go to automatic recode and recode this data, don't I?
For this one, no.
No? Okay.
That's for the independent test.
Okay.
So let me show you something. I don't think your textbook shows you this. What you can do, you can come here to compare means. And you
Right.
can just do paired sample t-tests.
Okay.
Because a lot of times, I think the textbook tells you to like compute a variable called difference and then
Mhm.
do a one sample t. But you can just do this.
Okay.
You just go here, and then,
You just
Put
move
that.
that there and then move that over there.
well, is that the right order? Because think about it, order matters. Like if you're doing a before or after, you can't do after before.
Right, okay.
So look at the question and figure out which order they're supposed to go in.
Good question.
Okay.
When I'm taking a t-test and I can find out my sigma,
Mhm.
can I switch my z-test or does it matter anymore?
So it's
you can't
90
really find
versus
something for t-test. What you
14
find
days.
is the sample standard deviation,
True.
which is different than
True.
the population.
Yeah.
So it's like that's the standard deviation for those 50 people or whoever you sample, but that doesn't say that's the standard deviation for, how many
Okay.
people in the population.
So, in order to do the z-test, I need to know the population standard deviation.
Yeah, at the beginning.
Okay.
There's like no way to find out the population
true.
standard deviation unless they just tell you what it is. If they're like, oh, it's this thing, you're like, okay, sweet.
So it says do 14 days minus 90 days.
Okay, yeah, perfect.
Okay.
Yep, so it says right there, so yeah, 14. Okay, or yeah, I can look
Let
at
me see.
options.
I want to make sure that was right.
Yep, it defaults to 95, so.
So my team is okay. I think it's because last night we did the automatic recode on the heat throw and we included that assumption.
Yeah,
That's
you
why I got the wrong
probably, I
answers.
think you guys must have done like an independent test or
Mhm.
something if you did the automatic recode.
Mhm.
So,
Okay, awesome.
see how that one's paired.
Thank you very much.
Do you have any questions there? I see you're working on something. So.
Yeah, I was just running through. I marked down questions that I had, like on homework quizzes and everything, but I think I
Figured it out?
understand.
Yeah, it looks like all the questions you've asked are on things you've already gotten right. So
Yeah, it's just.
you just want to understand it. Yeah. What's your last name?
Botta. B-O-T-T-A.
EOTTA. I just have to say who I tutored for them to pay me.
Sure.
Otherwise they will reject my thing actually. They won't pay me. But EOTTA.
Professor's going to
So
let us
I-
do. If we don't want to do the
100%
SPSS questions,
on
we
my
don't have to until we do the exam.
test
Hmm.
prep,
So that'll be
test,
nice.
I could get like a little bit score on that, right?
Yeah.
It means
so,
I know anything that's on the test.
so was that on your first attempt or your second attempt? For the test review. First attempt or first attempt?
Second.
That was your second one? Okay. So a good indicator of the score you'll get on the test is what you got your first time by yourself.
Okay.
Because like when you do it like this in a group where other people are talking to you, like you can kind of fix some of the mistakes.
Oh,
like
well,
the group
sometimes
helps
I do
each
it
other
again by
out.
myself.
Okay, so that's the
Okay.
thing. Like if you were to take it by
Uh-huh.
yourself, the first time around, like what score did you get? That's pretty similar to what you get on the test. Because the
Okay.
group reading quiz, like you have your group helping you, so like you might make a little mistake, and one of your group members will be like, "Oh, hey, we're supposed to do this," and
Yeah,
you fix
sure.
it. But on the test, you don't have that. It's just you.
Mm-hmm.
Okay.
So like if you can look at the group quiz and like know how to do everything right, then yeah, you can get a really good grade on
Okay.
the test because it'll be very similar to what's on
Okay.
that review.
Okay.
For chapter
Perfect.
15. Does anyone have any other questions? I know that this was supposed to go to 45, but we can go till 4. If you have more things you want to talk about.
So how does it work, like with the review from test 1 then? Like what percentage of?
10 maybe. The only things that'll be on there are questions about like type 1 and type 2 errors and like
That's
I'm
good.
trying to think what else.
That's what
But,
I should
like,
remember.
Very little from test 1
Oh yeah,
from unit 1 should be on this test. It's not cumulative, it's really just about unit 2.
but I thought it was for some reason.
It will be won't it for test 3?
For your last test it'll be cumulative.
Okay.
So unless your professor for the online class said like specifically this is a cumulative test, but 221 is designed to only have one cumulative test, the final. All the other ones are just
Because other kids told me that it was, so that's
Really?
why I was
Hmm.
like,
Yeah, that's weird. It shouldn't have been. Like, there are ideas that carry from test to test, like hypothesis testing, for example. Like, you won't stop doing this. You're going to be doing this kind of stuff the whole
Yeah.
class. Like, looking at sample size, looking at p-values, all that stuff.
Because I
But
think it even says like in the textbook, doesn't it say check for check review for test 1 or something like that in the textbook?
Yeah,
That's what I
it
was
does.
Yeah, so that's what I was like.
Yeah, I think
But I don't think my professor in his videos mentioned. Anything about-
it should be like 95% of it should be things from
Oh, me too.
Unit 2.
Oh,
Basically, yeah, it's like if there's anything from Unit 1, it'll be conceptual stuff like type 1, type 2 errors, and
Central
maybe
limit
like
theorem
central
and
limit theorem. That's another good one.
law of large numbers, and I think that's it.
So can we run through quickly
Yeah,
what
let's
would
do it.
be test 1 since I haven't looked at it forever?
No, that's all good. Let's do it. So, what's a type 1 and type 2 error? Does anyone here know?
I wrote it down somewhere. I gotta look at this.
Yeah, why don't you look through your notes, see if you can find anything
So
wrong.
type 1 error is that the null hypothesis is true, but we rejected it.
Okay.
Type 2 is false and we fail to reject.
So does that make sense? Like how that works?
I don't
So
know.
let's-
I just memorized the chart.
Okay, makes sense. Court of law. When you're doing criminal law, someone walks in and they're on trial for robbing a bank. There's this concept called innocent until proven guilty. That's like you are innocent of a crime until they can prove that you're guilty. So it's kind of like a null hypothesis. You walk into the court, and the null hypothesis is that you are innocent. Like that's just the truth. That's just how it is. And now they're trying to decide. Alternative is you're guilty, and they're going to go through. They're going to do a hypothesis test of sorts. They're going to run through and decide whether or not you're guilty. So, type 1 error. You have someone who is actually innocent. Like the null hypothesis is true. This person's innocent, but you say that they're guilty.
Yeah, we reject it.
You reject the null and you say, this person is guilty, even though they aren't. So that's a type 1 error. Type 2, you have a guilty person who you say they're not guilty. You should have rejected the null and said, this person is guilty, but you didn't. You did your test and you, for whatever reason, decided they weren't guilty. So I feel like that's the easiest way to do type 1, type 2 errors, to explain it.
Yeah, I just wrote it down like that.
Okay.
So
Now, does that
what-
make sense to everyone? Do you want like more of an explanation for type 1 or type 2 errors?
That's right.
So what else would be something that's on there?
Okay. Something else about this, they might ask,
about-
like, if the probability of a type 1 error goes up, what happens to the probability of a type 2 error? Goes down. Yep. Yep, it's inverse, so it's just like this. Where if one goes up, the other one goes down. Okay, yeah, that's perfect. Central limit theorem. What is the central limit theorem?
I don't know. I get mixed up with that and the large numbers. Yeah, I know. Like the large number has to be over 30, right?
Okay. So this is where it's kind of confusing.
Because
Because they both sound pretty
They
similar.
both talk about it being over 30. What? Brother Hathaway has a good way of teaching this. Moroni is professor, it's Brother Hathaway, and I'm actually the TA for that class. So. But what Brother Hathaway says, he'll get up in front of this class and he'll just do this. He'll be like, when I say central limit theorem, you say,
Normal.
and he does that over again. Central limit theorem?
Normal.
Central limit theorem?
Normal.
And so, what central limit theorem says, or I'll just abbreviate it. It says basically that, say I took a sample, I get an X bar, but I did that 1,000 times.
Are you guys just studying in here?
This is a group tutoring session for 221.
Okay. Okay.
Do you have is it reserved? Do you need?
No, I just need to go over a test with someone.
Okay, we're gonna be done at 2, so.
4.
Oh,
Four.
4. Sorry, I said 2, but
Okay,
yeah.
cool. Thanks.
So say you take, what time
It's
Yeah, 10 minutes.
Yeah, 10 minutes. Okay. We'll see if we take that one. Done before. So this is 1, but say you do this 1,000 times. So you have 1,000 different X bars. So you've taken 1,000 samples.
mm-hmm.
If you took the average of all of those samples, so the mean of the means,
Mm-hmm.
it would give you mu, the true population mean. So this idea, they'll use this phrase that the distribution of sample means. It'll say that. And basically what the central limit theorem does, like because this is true, if you have, and then we'll do law of large numbers actually as well. Law of large numbers basically says that if you take just one sample and you take, say, take 5,000 samples, like the bigger your n is, like as n goes up, your x bar for your sample is going to be a lot closer to mu.
What is X bar again? I forget.
The sample average.
Sample average.
And this is just an example. Like central limit theorem we can apply to like a lot of different things. So this is like for like a t-test or a z-test. This X bar.
And
But-
mu is just the sample mean.
This is sample, this is population. This is the mean for everybody. It's like, say we're talking about GPA. This could be like the GPA of the sample we took at BYU Idaho. This mu, that's the GPA for all college students.
It's the GPA for all, so that would be like the average for everything.
Yes, the average of everything. Let's put it that way. So what the central limit theorem does especially, I mean, the law of large numbers helps out with this, but basically, because of the central limit theorem, in this class, you can say, okay, if my n is bigger than 30, if n is bigger than or equal to 30, then my data is approximately normal. You know, it's not perfect, but it's good enough for me to do my test. And so you might have a question on the test that's like, it'll ask like, are the requirements met in a word question? And then there'll be like a couple of ways you can get to normality. Brother Hathaway, this professor from he uses this, he calls it the normality house. He says there are a couple ways you can get into the normality house. You can get in the window, or you can go in the door. So the door is like the central limit theorem. That's like if you have 30 or more in your sample size, or actually, we're going to put another window on. So this way, the main door is just that the data is normal. Because sometimes it'll say that. It'll give you like, you take a sample from a normally distributed population. And so like, in that situation, like I could take a sample of 3 things and it would still be normal because the whole population is normally distributed. It doesn't matter how many I take. So you can get into the normal house that way. With the central limit theorem, say you have a population that's skewed. One way it's, we'll say left skewed. It's left skewed. That's a great one. Left skewed. Thanks. So with this, it's like, okay, even though the data is left skewed, I'm going to take a sample of 100. And I can say that for like my test, when I'm using these 100 things, that group of 100 is basically normal. And I can get into the normal house. The other way you can do it is say you have like a sample of 28 or something. You have like, we'll say 25. And it didn't tell you that the data was normal, and it's not big enough to use the central limit theorem, but you can make some graphs or something. You can do like a QQ plot. You do your QQ plot, and they basically just line up. It's like picture perfect. And you're like, okay, cool. Yeah, that's normally distributed. Even though I have 25, like they line up, they look normal, and I can get into the normal house that way. But on the test, it'll have like a couple of correct answers. Like you can establish that it's normal, but it'll have 2 yeses. And one, it'll say like, oh, because the sample size is large, and one, because the data is normal. And only one of them is true. So like, so you just have to pay attention to that. Like look at the sample size and look at how you're getting to normality, because it'll probably ask you a question about that.
I just want to make a question
Okay.
about when I had enough information to something.
Sufficient evidence to
Yeah.
reject the null hypothesis.
There's always 4 options.
Okay. So this is a good question because you're going to get a lot of these on the test. Is it okay if I erase this?
Mhm.
So I'll post this to code in Aaron. When you finish a hypothesis test and you get certain results, how do you know whether you say like we have sufficient evidence or we have insufficient evidence, or what do you say with it?
P-value
Okay, p-value.
compared to level of significance.
Okay, so look at your p-value compared to the level of significance, so alpha. But can you be a little more specific than that? Like say you have a
So
p-value
it's-
that's like this.
If p-value is less, that's when we. I'm trying to remember. That's it.
If
Reject
p-value
null
is
if
low, you
p-value
check
is
the
less
HL,
than.
or you check the H.
So if the p-value is less than,
You reject null.
so usually so what would you say there? It's asking you to say like we have sufficient evidence or we have insufficient evidence. What do you say in this situation?
So let's see. If it is lower, we say we have insufficient evidence. Right. If we reject the null, let's see.
Does that depend on what the hypothesis is?
So kind of.
If reject, we have sufficient evidence to say that. Oh, okay. Oh, okay. Sorry. Mix it up.
Yeah. So your hypothesis test will always look like this. It'll be like, okay, H0 mu is equal to something. Let's say H alternative mu is greater than, less than, or not equal to something. And so let's think about like the innocent and guilty thing again.
Okay.
So this is true, the guy's innocent. That's what you believe. But you get this evidence back and you have enough evidence to reject the null. So what do you say about the guy? So the null is that he's innocent and you get a low p-value.
So low p-value means that we reject the null. That means that he is guilty.
He's guilty, yeah.
We
So
have sufficient evidence to say
that he's
that
guilty.
Yeah, because we always state the alternative hypothesis.
Yeah, that's super important, what Aaron just said. If you reject the null, you always say we have sufficient evidence. If you fail to reject, you always say we have insufficient evidence.
Then always state the hypothesis.
And then, and it's always the alternative hypothesis. So if you say we were doing a greater than test and we got a p-value like this, you'd say we have sufficient evidence to suggest that the true mean, mu, is less than something. Or if it was a not equal to, you'd say we have sufficient evidence to suggest that the true mean is not equal to something. If you got a high p-value, Say we have insufficient evidence to suggest that the true mean mu is less than something. Does that make sense, Maroni? How you would go through that?
Okay, so if I have sufficient evidence, it means that I accept the null hypothesis.
Yeah. Kind
Yeah.
of. I mean, what you're saying is right, but not in this class. That's the thing that's
Okay.
hard. Is that like when you do the hypothesis test, you've already accepted the null. Like you're not talking about accepting or you don't talk about accepting this. It's about rejecting or not rejecting. Is the thing. So you're accepting or not accepting this, or rejecting or not rejecting this. But you always say rejecting or not rejecting. But if your mind likes the idea of accepting more, then think about the alternative. We either accept or don't accept the alternative.
Okay. Because like, if I have sufficient evidence, it's because I reject all the time.
Yeah, so you have sufficient evidence to accept the null hypothesis, which means you reject, or sorry, I said that wrong. You have sufficient evidence to accept the alternative hypothesis, which means you reject the null hypothesis. And they'll always want you to have that word reject. You don't ever say accept, you say reject always. But if you like that thought process of like accepting something, if you have a low p-value, you accept the null. If you have a high p-value, you do not accept the null, or the alternative. Goodness. Said that backwards both times.
So low p-value, I reject the null. Okay. Okay.
High p-value, fail to reject the null. Cool. It's 4 o'clock. Any last questions?
Do you have any like slides or anything like that's like more study material or convenient or anything like that?
No, the best study material I'd say is the quizzes, that kind of like what you were doing earlier, is just go over like the homework quizzes and see if there were any that you got wrong on them, like do them again and get them right. And if you got them right, kind of do what you did, where like look through it and be like, okay, do I understand like how did I do this and like how could I do it again? And if you feel really comfortable with the homework quizzes, like if you could be like, yeah, I could easily get 100 on all of these, then you'll do really well on the test. Because it's the same stuff, they just change out like the data set or the numbers.
Cool beans.